For our next example, I pulled a problem that is not in our book. I wanted to do an example where it's just a radical, it's not part of a fraction, just to show you what that would look like. So once again, the process begins by comparing the radical expression you have to one of the radical expressions in this table. And in this particular case, we have a constant value in the front and then minus an x squared. So with this next example, we're actually looking at taking this radical form and making this substitution. As you saw before, I'm going to save myself some space to do some work. So my a squared is being represented by 25 right now. Therefore, take the square root, and a has to be 5. Therefore, since my substitution is supposed to be to let x equal a sine of t, my x substitution will be 5 sine of t. And automatically, once you have that substitution set up, you need to calculate what the dx would be. And the derivative of this expression would be 5 cosine of t dt. Once I have that done, I'm ready to go over here to my integral and make that substitution. So I will have the integral. Underneath the square root sign, I keep the 25 minus, I replace the x squared with 5 sine of t, which will need to get squared. And I'm supposed to have my dx at the end, and my dx is 5 cosine of t dt. So again, just to avoid confusion, you're going to see I'm going to bring this part out in front, including letting my constant drift out in front of the integral symbol. And when you square 5 sine of t, you're going to square both the 5 and the sine of t, which gets us 25 sine of t, still with the dt. And again, you're going to see I have a common factor then. That should always be the case, and I'm going to want to factor that out. Next, we remember that we do have the rule that says if we have a product underneath our square root, we can separate it. So we're going to break this up into just square root of 25 and square root of 1 minus sine of t. And it just noticed I forgot to put my squared on there. So the square root of 25 is going to be 5, which means I'm going to have another factor of 5 to pull out in front. So I'm going to have a 5 times a 5 sitting here. I still have my cosine of t, and now that this is gone, I just have the square root of 1 minus sine squared of t dt. After you've done that, again, you're going to have something here that an identity can help with. So back off to the side we go. I'm going to remember that sine squared of t plus cosine squared of t equals 1. I will want to solve this identity to make it look like what's underneath my radical. So I would want to subtract sine squared of t on both sides, which would leave just cosine squared t on the left equals 1 minus sine squared t on the right. So I can replace 1 minus sine squared t with cosine squared t. And again, here's where the magic happens, because when I take the square root of something squared, I get just that original expression back. So really, I have 25 times the integral of cosine of t times cosine of t dt, which is of course the same as 25 times the integral of cosine squared t dt. Now, at this point, your substitution has worked its magic and given you a nice simpler integral. Now you have to know how to go from here, and this is where all your integration techniques are on the table. So u-sub, integration by parts, partial fraction stuff. Or you may remember we had reduction formulas for powers of a single trig function. So I'm going to go back to the video from last week where I gave you those reduction formulas, and I'm going to apply it here, letting my n value equal 2. So that will give me my constant of 25 stays in front. I'm going to set up big old brackets here because, of course, the reduction formula is rather lengthy. You're going to do cosine of n minus 1 of t times sine of t over your n value, which in this case, again, is 2, plus n minus 1 over n, so 2 minus 1 over 2, integral cosine n minus 2 t dt. So that is following the pattern of the reduction formula. Now I clean this up. So I'll have 25, and I have cosine of t sine of t over 2 plus 1/2. Now cosine to the 2 minus 2 power is cosine to the 0 power, and anything to the 0 power is just 1. So I'm integrating 1 dt. I now have a simple integral that I can evaluate, so I'm going to do that next. The integral of 1 dt will just become t, and I, of course, have that constant 1/2 in front. Now my integral is gone, so I have integrated my expression. The only trouble with it is that it has all these t's sitting here, and we want it in terms of x and not t. So to overcome that, we're going to go to our right triangle trig. We're going to create a right triangle, putting t as an angle in that triangle, and we're going to use this initial substitution to help us label the triangle. So I have x was equal to 5 sine of t, divide by 5 on both sides to make the fraction on the left, and then remember, SOHCAHTOA says that sine is the ratio of the opposite to the hypotenuse. So opposite t I will label x, the hypotenuse I will label 5. I'll use Pythagorean theorem to find the missing side. Now, in this case, be careful because we have the hypotenuse and that does need to go on the right. We're missing one of either a or b, whichever one you want to leave blank, plus x squared. I'm going to solve for a squared, so I'm going to move the x squared to the other side, giving me a squared equals 5 squared is 25 minus x squared. Take the square root, and I get that side A would be the square root of 25 minus x squared. So that belongs on this side of my triangle. Now I need to go through and read all the substitutions that I require. In other words, any expressions that contain t. I have cosine of t, which I do not have a substitution for, so I need to do that. Sine of t, I already do have the substitution to use. Sine of t is just x over 5. And I have a plain old t here, so that introduces a new wrinkle as well. First, let's just take care of the cosine of t. Using my right triangle and the fact that cosine is always the ratio of an adjacent side to its hypotenuse, adjacent to angle t is this side, square root of 25 minus x squared, over the hypotenuse, which was 5. So I now have a substitution to use for cosine of t, which will be all of this. And as we said before, I also need a substitution for t. Now to do that, you're going to go back to your sine of t statement, and you want to solve for t. Okay, now remember here, this is sine of an angle. To get the angle by itself, you always do the inverse of that trig function. So I'm using inverse sine of whatever fraction it was equal to. So to solve for t, you're not doing something crazy like trying to divide by sin. You can't separate the angle from its trig function that way. What you do is use the opposite operation. So the opposite of taking the sine of t is to take the inverse sine. And again, you always take it of whatever your fractional ratio was. So this now gives me a substitution for t. I'm going to go back to my antiderivative and substitute all of these pieces in. And last, I'll want to distribute this constant of 25 into both the first term and the second term. And something nice happens here in the first term because I've got a 5 times a 5 in the bottom of the numerator, which can cancel with this 25 here. 5 times 5 is 25, so I can cancel this 25 with the 25 in front, leaving me with just 25 minus x squared times x, I'll put that x in front, over 2. Now, I crossed out that 25 because I canceled it, but of course I do need to distribute that 25 also to the second part. So I'm going to do 25 times the numerator of this fraction, which is 1, so we get 25 over 2 inverse sine of x over 5 plus c. And once I have an expression that's completely x's and no longer any t's, this is my proper antiderivative. Now again, this is what I was saying before about if you were to type this in Mathematica and start with this thing here, and it were to spit out this to you, you might be like, whoa, I must have done something wrong. So it's important to learn the techniques by hand so that you're a better judge, if you do go to use software, of whether or not what the software is telling you is reasonable, or perhaps you had a typo instead. All right, I'm going to do a couple more examples just again because this is a very long, involved process and different things can come up in the middle of these problems. So I'm trying to choose some that have a nice variety in them. So we're back to, in this case, an integral that has a fraction in it. I'm going to begin by comparing my radical form to those in the table. And mine looks the same this time as this first one does that I highlighted. I have a constant first minus my x squared. So I'm going to be using the substitution a sine t. So in my problem, a squared is 9, giving me a will be 3. My substitution is supposed to be a sine t. So my substitution is going to be 3 sine t. And at some point, you'll probably start to condense some of these steps together, and that's totally fine. Just do as much as you need to do to get through the problem. You do need to show work, but some simplification steps you can kind of do in your head. And when I take the derivative of the x, derivative of sine becomes cosine. So now I'm ready to write my integral as a t integral. In the numerator, I have an x cubed sitting here, so that does mean I need to take my x substitution and cube it. So 3 sine of t needs to get cubed. And I have the dx sitting up there, so I need to put in a 3 cosine t dt next to that. So that's my whole numerator, which again looks intimidating, but remember, trig substitution is magic. Bottom, I'm going to have 9 minus my x squared. Okay, in both the numerator and the denominator, when I raise a product to a power, I'm going to distribute that power to both parts. So that will be my next step. Once I've done that, in the numerator, I've got 3 cubed and I have another 3 sitting in the numerator, so I can actually bump that up to 3 to the 4th. And you're going to notice I'm not going to bother multiplying that out because I'm going to get some factors to cancel, and it turns out just to be easier to leave it in this exponential form. So I actually have a 3 to the 4th power that I can take out of the whole integral, leaving behind in the numerator just sine cubed t times cosine of t dt. And in my denominator, as usual, I now can factor out a 9 from both terms. And remember, square root of 9 I can do separately, which is 3. And because it's in the bottom of the fraction, it's going to cancel out one of my 3's in front of my integral. So skipping a couple of steps there, I'm going to make it 3 cubed integral sine cubed t times cosine t dt all over the square root. So I've taken this 9 out as a 3, and again, because it was underneath, I just reduced that exponential expression. And now I have 1 minus sine squared t left. And you look at what's under the radical, you pull up a related identity. So sine squared t plus cosine squared t is 1. Again, you want to solve this identity so it matches what's underneath here. So if I subtract sine squared t over to the other side, I have cosine squared t equals 1 minus sine squared t. Now, after you do enough of these, if you're just automatically going to know, oh, I can change this to cosine squared t, that's fine. You don't have to show this work off to the side. It's really your level of comfort. I have 3 cubed. I have the integral. Numerator stays the same. And now my denominator becomes the square root of just cosine squared. We have reached the magic step. The squaring and the square root undo each other. So finally, I have gotten to sine cubed t times cosine of t dt. And you can see how even more magic is going to happen because that cosine t in the bottom can cancel with the 1 in the numerator. So the radical is gone, and I am now left with the integral just of sine cubed t dt. All right, at this point, you have to throw all the integration techniques you know at this problem and figure out how you're going to integrate sine cubed t dt. There is a reduction formula for powers of trig functions. So I'm going to go ahead and let my n value be 3, and I'm going to write out the reduction formula version of this. So I went through the reduction formula, and everywhere there was an n, I substituted in 3. I'm now going to go through and clean things up. So the reduction formula did what it was supposed to. It changed our integral into a simpler expression to integrate. And the integral of sine is negative cosine. At this point, my integration is done, but I think before going and changing my t expressions out for x expressions, I'm going to go ahead and do some cleaning up of all these constants. So I have this 3 cubed in front, and I have 2 terms on the inside. I have this one here, and then this one here. Both terms do have a 3 in the bottom, so I can cancel that with one of my 3's here. So this 3 cubed, I'm now going to reduce to a 3 squared. That gets rid of the 3 here, gets rid of the 3 here, so I'm really just left with minus sine squared t cosine t minus 2 cosine t plus c. And there's no significance here for me changing to square brackets versus round ones. I don't know, I seem to prefer square around things that have fractions and round when they don't. There's no rule about that in the universe, though. That's just my own little weird preference. Now I'm going to go ahead and distribute, I guess, my constant in. So this is really just 3 squared. So you can see how I didn't need to calculate 3 to the 4th because ultimately I'm just left with 3 squared, which is 9. So I have minus 9 sine squared t cosine t minus 9 times 2 is 18 cosine t plus c. Next, I need to get all of these t expressions out of here. So right triangle trig time. Let your original substitution guide how you label your triangle. It was 3 sine of t, divide the 3 over, I get x over 3 is sine of t. So there are my labels for my opposite and my hypotenuse. Opposite t is x, hypotenuse is 3. I do Pythagorean theorem to find the missing side. And once I have my triangle completely labeled, now I should be able to get any t values I might need for my antiderivative. I need sine squared, which is fine. I have sine of t, so I can just square that. That's not a problem. The one I'm missing is cosine of t, which would be adjacent over hypotenuse. Adjacent is 9 minus x squared over hypotenuse is 3. So this is the substitution I'm going to use for my cosine. And I have a substitution for sine, and that's all I needed. I'm going to put that in. So I have -9. If I square my sine, I need to square the numerator and the denominator here. So I'm going to have times x squared over 3 squared, or 9. You can see how convenient that's working out. That's my sine squared times cosine minus 18 cosine of t. And I'm just going to clean up the rest of the constants that are laying around here. So my first term becomes -x squared, square root of 9 minus x squared all over 3. I can reduce between the 3 and the 18 in my second term, becoming 6 radical 9 minus x squared plus c. We survived another one.